Okay, so just finishing number 9 there. 9 part C. So you fill in all your numbers. Now when you get to the coefficients for the first one, it's 0.3 because that's the kinetic coefficient for the first one. And for the second one, it's 0.2 because that's the kinetic coefficient for the second one. And then your mass for M3 is the 44.722 because you've added the 5 kilograms to it. And when you punch all of this in, you should get an acceleration of 0.966 meters per second squared. Okay? So that finishes that sheet. Hopefully all is good. Now, in one class yesterday, I gave this example. And in the other class, you didn't see it. And some of you so first period didn't see it at all. Third period, some of you didn't get to it. So if you didn't get to it, you need to do it. It is very similar to number 9. The question is, what is the range of values for M3 to keep this hanging stationary? Okay, so M1 is 20 kilograms, M2 is 40 kilograms. The coefficient of friction on M2, which is static, is 0.4. The angle is 30 degrees. And what is the range of values for M3? So again, it means you need to do it twice. Once going down the incline and once going up the incline. Okay, so if you didn't try it, I want you to try it. The answers are 26.1436 kilograms is the lower end. So M3 has to be bigger than it, and it has to be smaller than 53.8564 kilograms. Okay, so try it and see if you can get it, please. Some of you got it yesterday in class, the rest of you give it a shot. Okay, and it's just like number 9. The second question of these that I want you to work on, and we are going to go to something new here too, but the second question I want you to work on, which is example 4, which no one got to yesterday, is another multiple mass looking like this, M1 hanging down, and M1's mass is 10 kilograms. Okay, M2's on the surface, its mass is 20 kilograms. M3 is hanging down the upper side, it's 30 kilograms. Coefficient of friction for M2 is 0.3. The acceleration is 2.5 meters per second up the incline. Okay, so it's up the incline. And what I want you to find, and you're going to love this, is a friend decides to help. Of course, they didn't take physics. So they push directly into the incline. So there's going to be a component of their force going up, Fx, a component of their force going into the incline, Fy. This, of course, will also be 30. I want you to find this force. Okay? So give it a shot. Remember that it's going to make the normal on M2 different, but you still do the same thing. This way will be positive because it's going up the incline. And so remember, there'll be friction on M2, and there'll also be an M2GX. If you do it correctly, you should get an F of 143.674 newtons. Okay? So that's question 2 of your homework. This is question 1 if you haven't already done it. This is question 2. None of you have done this one. Okay? All right, so give that a try. Where we're moving now is our new unit. So tomorrow we'll go over those 2 questions. You have an assignment that you're working on, and we'll be ready for a test. I would suggest Thursday or Friday because I'm pretty sure you don't want it tomorrow. It'll start with the inclined plane questions where Buddy was pushing into the incline, because remember I didn't give you one of those, not multiple mass, but just one like that. Then it'll include Atwood machines, and then like ones where it's on a flat surface with multiple blocks, and then incline ones. Okay? So Thursday or Friday, and we can figure it out tomorrow. Our next unit is called Static Equilibrium and Torque. It is really the first totally new thing. You haven't seen this in grade 11. You've probably heard the word torque before. You would have heard it if you're into cars. People often talk about torque wrenches or how much torque a motor can generate. Maybe with a hockey stick, people will talk about the torque you generate when you're hitting. Okay? So usually if we were in class, I would ask you what it is, and some people might have a feel for it but not actually be able to explain it. So, the symbol for torque, the letter, is the capital Greek letter T. It's called a tau, T-A-U. Okay? And I have some notes that I will give you like written out. So if you just want to watch this a few times to get it, and then I'll give you the notes the next time I see you. So if you think about it, up until now, we've had a box, and we've always been, when we do the sum of the forces, we always do it, we assume the box is like a point mass. So we say, okay, one person's going to put 100 newtons going this way, let's say east, and the other person's going to put 100 newtons west. And when we as soon as we see that, we know this box isn't moving. Okay? The reality is, though, not all objects are point masses. For example, if I had a meter stick or a person, and if we were in class, I would use a person. But if one person, let's suppose we have someone standing in the front of the room, okay? One person could push on that person with a force of 100 newtons east. And the other person, if they pushed up here, it would just be balanced out. But what if they pushed down here? Now these two forces are not going through the same point. And because they're not going through the same point, they're not just going to cancel each other out. So we've always been considering objects that we assumed were called point masses, that all of their mass was concentrated at one point, and that's where the forces went through. But in real life, we're not all point masses. We have dimensions. And so if the forces aren't going through the same spot, the sum of the forces will still be zero, but this object will move. Imagine if I hooked this person by their belt loop on a peg, this person would then spin. What that means is that we have to pause and think about motion again. When an object is moving back and forth in a straight line, like these forces would cause, it's called translational motion. And so here there would be no translational motion, and here there wouldn't either. It isn't going to move this way. Think about in math when you did translational transformations, like when you move them, horizontal translations, okay, or vertical translations. But this one, it's not moving in that way. Instead, it's rotating. It's called rotational motion. And so something can have no translational motion, but could have rotational motion. Something could have the sum of the forces, could be zero, like they are here, 100 minus 100. But there could still be rotational motion, and that's where torque comes in. Okay, so before we get to torque, we have to go back and look at equilibrium. Up until now, we assumed something was in equilibrium if the sum of the forces was zero. If the sum of the forces is zero, then this is called translational equilibrium. It means that the whole object is not moving from one location to another. But you could have translational equilibrium and not rotational equilibrium. In order to have rotational equilibrium, it's not just the sum of the forces that has to be zero, it's the sum of the torques that must be zero too. Okay? So here the sum of the forces is zero, but not the sum of the torques. Okay? When you have both of these, then we say the object is in static equilibrium. Okay? Static equilibrium. So then what the heck is torque? Well, torque is generated by a force. It's not a force, but it's generated by a force. and that force is acting on an object